we look at this. We have two scatter plot overlapped in one figure. For the first one, we look at the red dot. This, and all this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 numbers here. And we know, recall from what we just discussed, the correlation coefficient for the red line will be the R equals, looks like all the points are on the straight line. So the correlation is very strong. The strength is 1, and it's positive. The larger the x, the larger the y. So that's why it equals a positive one. So this is for the, we use a different color. So for the red line, R equals a positive 1. And for the blue line, and we see R equals also equals positive 1. The reason is all the points are again on the line, so the strength is strong, which equals 1, and is also positive. But definitely these two lines are different. Although both are the larger the x, the larger the y, but they have a different rate. For example, here, with the increase of x, the red line increases faster than the blue line. So that gives us a hint that only the correlation coefficient is not enough to describe a set of data. Sometimes we need more, and this new concept is called a regression line. The purpose for the regression line is, for example, if I want to predict the y value from x. In this case, we are given this, for example, we take this red line as an example. If I want to know if x equals somewhere here, if x somewhere here, what is this y value? What is this y value if x equals here? If we are given this line in form of a line equation, then we can easily predict this value, because y can be calculated from the x value here. So this is called a regression line. A regression line is a straight line that describes how a response variable y changes as an explanatory variable x changes. In this example, with the increase of x, y changes faster than y. In regression line, we need to distinguish between the x and the y. Because if we plot same set of data with the x and the y switched, we are going to have different lines. For example, here, let me suppose this line here, y equals 2x, and if we draw it to look like this, the slope equals 2. Instead, if we want to draw, so this is x, this is y. Instead, if we want to draw a function of x as a function of y, so that means we want to draw this is y, this is x. Then from here we know x equals half y, so x equals half y. So x equals half y, it will be like this. So we can see this line and this line are different. So if we switch the position of switch the order of x and y, we are going to have a different result. That gives a hint. When we calculate the regression line, when we describe a regression line, we need to distinguish between x and y. You cannot ignore this. So the next, we are going to find the line if we are given this set of data. If we are given this, or this set of data, then we need to find the line here in form of a line equation. Right. Now the data set is given in this scatter plot as this blue dot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, maybe may equals 20 here. We know regression line in our class is a straight line. We can have several, actually infinite straight lines try to pass through this data set. For example, this red line, this blue line, this green line, and this purple line. Now the question is, which one is better? Or which one is the best? So we try to find the best regression line. When we discuss the best regression line, we need to have a standard. What do we mean it is the best? Okay, first one, we use this one as example here. Suppose the data set is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. This 15 data set pairs of data here. And if by any method we draw a straight line, try to pass through this data set. This is the linear form here. And for any, we do not expect this straight line will pass all the points. Right? Just like this. This is more general. Okay, now for this point here, we can see for this point corresponding x value equals 3. This point also corresponding x value of 3. But if we know this line here, now we have this point is on the line. If we know the line equation, we plug x equals 3 inside the line equation, then we can have a y value here. This is the y value. And we call this one as the predicted value. We use a y hat to represent. The actual value here, or the actual value here, we call this observed value. There's a difference between the observed value and the predicted value. And we call that a residual. We are going to discuss in the next slides. But here it just says the distance to the line. So the distance to the line for this point here, the observed value here equals 0.07. And the predicted y value equals 0.048. Then the distance will be the observed minus the predicted. Always use the observed minus predicted. This is called the residual. In this value here, the residual equals 0.032, which is positive. That means this observed point is above the straight line. In contrast, this point, the observed value equals 0.02 here. Again, the predicted value is the same, 0.048. And the distance of the observed to the line is negative 0.028. Negative because the observed point is under the straight line. For a straight line, regression line, to be best, we want these errors. The errors means this residual here. Definitely, we predict this, but the actual value is here. So this part here is the error, and this one is also the error. And the same thing for this. This part here is error. This one here, all these are errors. Okay, this one has no error because this point is exactly on the line. So the error for this part, the residual or the error is 0. So this one has no residual, no error. For a line to be best, we want all these errors add up together to be as small as possible. So this is one concept of the best regression line. So the sum of all the residuals to be equal to 0. Now we look at another example. For example, this line here, one point is here, another point is here, another point is here. So this is this line passes through this point, and it's perfect. And the residuals are equal to 0. This residual is equal to 0, this residual is equal to 0, this residual equals 0, so the sum is still equal to 0. We can also, for this same 3 point, we can draw a line like this. We can draw another line like this, We said this one is also the best regression line. The reason is the residual here equals to 0, the residual here equals negative, but the residual here will be positive, because they are symmetric, so they cancel each other. So again, the sum of all this yi minus predicted, all this I will be equal to 0. So this one is also the best line. It looks like any line passing through this point will be best based on our standard. The standard is the sum of all the residuals equal to 0. So this one is not good standard. Instead, we are going to use the residual squared. So that's why it's called, there's a square here. We are going to find the error, but we do not consider the positive or negative. Instead, we consider all this as a square, the absolute value square. We want this sum to be as small as possible. Now look at this example here. This difference is 0. This difference is 0. This difference is 0. Squared still all 0. So the sum equals 0. So this one, the sum equals 0. But for this one, this residual equals 0. It's good. This one equals negative, but after the square, this is positive. And this one, positive square, also positive. Then add up together, this line, the sum of the residual squared will be larger than 0. So based on our new standard, this one is the best line. And this is called least square regression line. So now look at this. Suppose the green line is claimed to be the least square regression line. What does that mean? That means among these 4 lines, the green line has the minimum sum of the squares of the residuals. For this point, we find the residual, this one, residual, this residual, all positive or negative, or even or 0. Then we square it, add up together. For each line, we have this sum. So this one has a sum, this one has a sum, this one has a sum, this one has a sum. And the green line has the minimum sum, sum. So this is called the least square regression line. We just discussed the meaning of a least square regression line, and we know this one is very, very important. When we discuss curve fitting for straight line regression, and most probably we are going to use the least square regression line in the least square sense. Okay, now we know which line we want to find, so how to determine the line equation? If we are given a straight line, we want to describe this line. We need to use the line equation. And from math, we know there are lots of forms for line equations. One of them is the the slope y-intercept form. Slope y-intercept form is y equals and mx plus b. And the b is called the y-intercept. Y-intercept means the line intercept with the y-axis. So in this example here, and this is the y-intercept. Slope is m. Slope means here the tangent of this angle here. This angle is theta. So then this slope equals the tangent of this theta, and this one equals m. In this example, it looks like this angle is equals close to 45 degrees, so this may be equals to 1. That means the slope is positive. If we know the y-intercept and the slope, then we can easily write out the line equation in the slope y-intercept form. So now the question is very clear. If we are given the data set, we just try to find the slope of the regression line, and we also need to find the y-intercept. These formulas can be derived from math, but we don't want to bother you with all this, and instead we just list the formulas here for you to use. Suppose the line equation is given like this: y hat equals b0 plus b1x. Here b1 is the slope. Right? We can use b1 here. And in math we may use m, or somebody may use k. That doesn't matter. Right? The b0 here is the y-intercept. Right? And usually you just use b. But here in this class we use b0. How to find this b0 and b1 to get this straight line? Right. The first one is we try to find the b1, which is the slope. The b1 is defined as r times sigma y divided by sigma x. What is r? R is the correlation coefficient. Sigma y is the standard deviation for the y data set, and the sigma x is the standard deviation for x data set. So if we are given all these points, we know we have an x data set, we have a y data set. We calculate the sigma y and the sigma x. Then we calculate the correlation coefficient, and we know how to do this. We use the example to show how to calculate the correlation coefficient. And for correlation coefficient, we need to calculate the mean of the x, the mean of the y, the sigma x of x, the x and the sigma y for the y data, and we need to calculate the z-scores for all the x points for all the y, and then multiply together, then add up together, then divided by n minus 1. Right? That gives us the r. So once we know r, and we definitely know sigma y and sigma x, then we just sigma y over sigma x, then times r gives us the b0. Right? So this is how we calculate the slope. The next one is to try to find the y-intercept. The y-intercept will be equal to y bar minus b1 times x bar. X bar is the mean of x, y bar is the mean of y, and b1 is calculated from here. So that's why we calculate b1 first, then we calculate b0 second. Once we calculate b1 and b0, we plug into here, then we get the line. It's very simple. In the homework or in the test, if I ask you to calculate the line equation, the least squares regression line, then you need to follow these steps to do it. Right? I know you have calculators again, you can use just several functions, then you calculate all these lines. But I don't want you to do that. You need to practice to try to understand the meaning of this first. Later time for big data set, definitely we do not use this step-by-step method. You can use that functions to do it. Or if you want to write your code to calculate by yourself, we have a lot of variations that can be used to calculate the slope and something else. Right? And other textbooks also have different formulas, but they must come to the same conclusion. So we prefer use this one and use this one. In concept, they are very clear, right? Because so far we discussed the z-score concept, we discussed the mean, the standard deviation, the correlation coefficient, and this least square regression line combined all this together. Next slide, we are going to use an example to show how to step by step calculate the least square regression line. Right here, this example we already discussed this example. This example we use to calculate the correlation coefficient. So we can just borrow some numbers from there. The data set is, first one is 1, 2, so 1, 2 is here. The next one is 2, 5, so 2, 5. And the next one is 3, 6, so 3, 6, 4, 8, and so on. So we have this all data set on the scatter plot. And we try to find this red line, which is the least squares regression line. And we need to find the slope and the y-intercept. So far, we should be very clear that how to do this. Calculate the mean of x, the mean of y, the standard deviation of x, the standard deviation of y, and calculate the correlation coefficient, then calculate the B1, then last calculate B0, then that's it. Okay. From the previous example, we know x bar, the mean of x equals 5.5, y bar equals 11.7. Everything is in the first few slides. And sigma x equals 3 something, sigma y equals 6 something, and the correlation coefficient equals 99% and something. Right? The next one is to calculate the slope of the regression line, which is B1. And by definition, B1 equals R times sigma y over sigma x. And R is here, and sigma y is here, sigma x is here. So we plug into these three numbers, we get 2.0909. So this is B1, and for B0 equals y bar, and y bar is here, and B1 is calculated already, we obtained from here, and x bar is here. So we plug into numbers again, we get y-intercept equals 0.2. Now we should draw this line. Draw this line, first line you need to find the y-intercept. Okay, so here, it's very small, just about a little bit, 0.2 above the origin, so that's 0.2 here. Then the slope equals almost equals 2. Then we just use a ruler to draw this straight line. And this straight line is called the least squares regression line. So that's how we calculate this line. And again, we should understand the physical meaning for this. The regression line for here, for example, the residual for this one is negative. Right? This value minus the predicted. Right? And this value looks like it's on the line. So the residual equals 0. This one positive, positive, negative, positive, negative, negative, positive, and negative. All these residual squares first, then add up together, give us a sum. And this sum is the smallest among all the lines, all straight lines. This, no matter how your straight line is, this red line is the smallest. So that's why it's called the best. It's the least square regression line. Least square regression line is important. We can use this to do something. The first one is to making prediction with the interpolation method. Recall that we discussed this example before. The number of beers on the x and the blood alcohol level on the y, and we have this scatter plot like this. Now, because we are given these x values and we are given these y values, we can easily use the method we discussed as in the example to calculate the regression line. And this line is given by this. The line is y hat equals 0.0144 x plus 0.0008. So the y-intercept equals this, the slope equals this. So this black line is the least square regression line. Right? We ignore the details, the procedure how to do this, but you should be able to easily to calculate the regression line. Suppose we know this regression line. We are going to use this line to make some predictions. For example, in this test, this experiment, we know if you drink one beer, the predicted alcohol level it will be here on the line, but the actual one is here. If you drink 2 beers, and it is this, looks like it's on the line. And if you drink 8 beers, it is like here, very close on the predicted line. But how about if you drink 6.5? 6.5 is here. We know we didn't do this example. We didn't test this in the experiment. But if I want to know if you drink 6.5 beers, what is your blood alcohol level? That's easy. We can just predict here with this regression line. So we claim that this point corresponding to x equals 6.5 on this line here, and this corresponding y value here is our predicted alcohol level. So what we do is, because we have this line, y hat equals this, x plus this, we just make x equals 6.5. We plug x equals 6.5 into this here, then we have this predicted value. So 0.0144 times 6.5, then plus 0.0008, and this value is calculated as 0.094 milligram per milliliter. And this is the predicted, the expected value here. Although we didn't do this experiment, but we can predict if you drink 6.5 beers, your alcohol level will be close to this. So this is a prediction. But keep in mind, look at this. This number looks like a reasonable. The reason is this 6.5 is within the range of our experiment. The range of our experiment, the minimum equals 1. We never done anything smaller than 1. The maximum is 8 here. We never done anything that's larger than 8. So the minimum is 1 and the maximum is 8. So the range is between 1 and 8. And this 6.5 is within this range. So it's inside the range, so that's why it's called interpolation. And interpolation, the result obtained from interpolation usually is reliable. So we can use this method to make some predictions. Next one, how about if I ask, what is the blood alcohol level if you drink 100 beers? Right? If you drink 100 beers, it says easy. Okay, we just plug into here, plus, okay, x equals 100, then plus this. So x equals 100, okay, then y hat equals 100 here, then that will be 1.44, so it equals 1.44 something. And we know this number is ridiculous, right? Because this one is 1.44 milligram per, this is too much. So you may ask, okay, this result may be not correct. Right? You're right, this result is not reliable, and we have other considerations. So for example here, another example is you want to predict how tall you will be after some years. For example, we have an experiment here. For a kid, okay, so 3 years old, that's the height is 35. So 4 equals like 36 or 37. 5 years old equals like 42 or something, and we have some result here. Until 15 years old, the height equals like 65 something. Now we want to predict, how about when you are 22? How about when you are 30 years old? How tall will you be? Okay, we plug into this line and we see when you are 22, you are going to 85 inches. That's maybe, right? But how about when you are 30, your height will be close to 105. Okay, that will be 105 inches, that equals 8, 9, okay, close to 9 feet. Right? So that looks like ridiculous, not impossible. Right? So what is the problem? The problem is here. If you do this experiment, the actual data is supposed to be like this. Instead of going straight up, it will flat. So that means this regression line is not very accurate. Right? So what's the problem with this prediction? Right? Look at here, in the experiment, our range of data, the range for the data is from 3 to 15, that's all. But you predict your age equals 22 or even 30. These ages are outside this the range. So that is called extrapolation. Here. And as we already know, we can see from here, prediction from extrapolation is not reliable. So if you want to make predictions from extrapolation, so you need to be very careful. This may not be correct. You may ask, how about I still want to use this method how to predict with this? We can still predict, right? Okay. There are a lot of ways to do this. So this part is beyond this class. I just mention, if you are interested, we can discuss. I won't test you anything like this. For example, you can not necessarily use linear interpolation. You can use, for example, the regression line, not straight. You can use a second order, a curve, like this one. You can use this one to predict. So that is one way. The other way is you can use a piecewise linear. So if the age is below 15, so you use this straight line. If the age is above 15 to maybe 25, you use this straight line. Maybe after something like 30 something, okay, this is almost straight. You never grow up taller again. So maybe just flat or even lower. Okay, so you can use piecewise linear. This part is linear. This part is linear. This part is linear. Use this segment by segment. It's called piecewise linear prediction. So this works too. But anyway, the point here is you do not want to use extrapolation for reliable prediction. We just discussed the correlation coefficient and the regression line. Looks like these two are different, but there are some relationship between these two. In this slide, we discuss in detail, a little bit in detail, the meaning of this. The correlation coefficient measures the spread, the scatter, in both the x and the y directions. In a linear relationship, we only work for linear relationship. If it's not linear, okay, we don't care. We cannot use this method. So the relationship must be linear. And we know we deal with multiplication of the z-scores. For regression line, we need to know the slope and the y-intercept. The slope is calculated by r times sigma y over sigma x. And the y-intercept is calculated by y bar equal minus b1 times x bar. So the regression line can be given as y equals b1 x plus b0. Let's see what exactly this means. In a simple example, Suppose the y-intercept equals to 0. So b plus b1 here, suppose plus b0 here. But we assume b0 equals to 0, so this one is gone. So only y equals b1 slope times x. So that means this line passes through the origin. Y equals b1 times x, and b1 equals this one. We plug into here, so y equals r times sigma y, and sigma y move from this side to this side, and x, sigma x is still here, this x is here. So we have this relationship. So y divided by sigma y equals r times x over sigma x. Right? This formula can give us some thought. Right? This r is correlation coefficient. This x is the data, and x divided by standard deviation. That is like how many standard deviations of x is, or the x value in the unit of standard deviation. Now, for example, I said there's a test. There's a test here. The average of the class is 85, and now you get 90. Somebody get 80. Somebody get 75. Somebody have 95. And we said this the standard deviation suppose equals 5. Then this one here, if we minus mu, the average is here. Then this one will be equals to 1 standard deviation. This will be 2 standard deviation. This is -1. This is -2. But we are going to use this score, not this score. Sorry, the x in terms of the standard deviation. We assume the standard deviation equals 5. So if you get 90, that means your x over standard deviation equals 18. And this average here is x over standard deviation here, and will be equals to 17, and so on. So we instead use the scores, the point. We use the standard deviation as the unit. So we can see the class average is 17. 17 what? Not 17 point. 17 standard deviation. And your score is 90. We do not use 90 point. We use 18. 18 in unit of a standard deviation. So this one is here. See? And this is x divided by sigma x. That means the x value in unit of sigma x. And this is also y value in unit of sigma y. And this y value in unit of sigma y is related to this x value in unit of sigma x with this factor, the r. So for example, if r equals 1, that means the y will be equal to x, both in unit of the standard deviation. If this one here, r equals 0.5, that means for every x in unit of sigma x, the y will be equal to half of that value in unit of sigma y. We are not seeing here if r, for example, if r equals 0.5, we are not seeing y equals 0.5x. We do not see y equals 0.5x. This one is not correct. Instead, we said y in the unit of sigma y is 0.5x in the unit of sigma x. So we can see this here is how this correlation and the regression related. So there are some relationship between these two. Okay? The next concept is called the coefficient of determination. Now we go back to this example again. We are given these two data sets, and we plot them with this scatter plot, and we can find this least square regression line. Now, we may ask questions. Right? This example is the previous, the beer and the blood alcohol level example. We know X has variations, has variance from here, from 1, 2, 3, 4, they have variance. And the Y value, the alcohol level, also have variance. I may ask a question, why the Y has variance? We may consider, okay, that is because the X has a variance. Then look at this way. Look at this one and this one. The variance from here to here, the X is increased by 1. But the Y value not increased, actually decreased. So that means the variance of Y cannot completely explained by the variance in the X. If we can explain all the Y variance by the X variance, that means the larger the X, the larger the Y. The smaller the X, the smaller the Y. But this looks like here, or some even here, look. The Y, the X does not change, but the Y changes. Even there's no variance in X, we still have variance in Y. So it looks like the Y variance cannot be explained totally, 100% by the variance in X. So how much of the Y variance can be explained by the variance in X? Right? That is called the coefficient of determination. And luckily, that is just the R squared. We call this coefficient of determination as R squared, and this represented by R squared. So what is R squared? Is this any relationship between this R is the correlation coefficient? Yes, that R is the correlation coefficient. So if we know the correlation coefficient, then R squared is called the coefficient of determination. And its meaning is the variance of the predicted value Y divided by the variance of the observed value Y. Or the variance in Y that can be explained by variance in X. Now let's use one example to show how to understand this coefficient of determination. Here, we assume we have only 3 pairs of data. The first point is 1, 1, second point is 2, 2, the next point is 3, 3. If we draw this 1, 1 here, 2, 2 here, 3, 3 here, okay, if you draw the line, okay, perfect. The line passes through all the points. Now let's calculate with our formulas. X bar, 1, 2, 3 equals 2. Standard deviation, 1 minus 2 squared plus 2 minus 2 squared plus 3 minus 2 squared equals 2. Then divided by 3 minus 1, okay, equals 1. So sigma x equals 1. And zx will be this one minus the mean divided by this. So zx, zx again equals x minus mu over sigma here. And zx, the first one is 1 minus 2 equals negative 1 divided by 1. Okay, equals negative 1. The second one, 2, minus 2, then divided by 1 equals 0. The last one equals 1. And for the y, 1, 2, 3, same thing here. So we just copy all these numbers. And the correlation coefficient R, plug into numbers. All this goes this times this plus this times this plus this times this, so equals 2, then divide by 2, okay, equals 1. So this R equals 1. And R equals 1, then the slope equals R times sigma y. Sigma y is here, sigma x is here, so 1, 1, 1 here, okay, that equals 1. And B0 equals 1. So the least square regression line will be equals y hat equals x plus 0. So y hat equals x. We plug into this. This is the origin. So there's no. This one is -1. This is origin. So this is y equals x. So that's the first one. Now we are given the second data set. 1, 1, 2, 5, 3, 3. So 1, 1 is here, 2, 5 is here, 3, 3 is here. Looks like these 3 points are not on the straight line. We need to use a regression line. So again, we follow the same steps. X bar equals 2, 1, 2, 3, and sigma x, zx, or this. Y bar equals 1, 5, 3. Okay, 3, this, everything here. And we calculate for this point, for this example, the r equals 0.5. And the b1 slope equals 1, and the y-intercept equals this equals 1. So the line here equals this one. And this one equals here. So we have the correlation coefficient equals 0.5, and the regression line y hat equals x plus 1. And if we plot this here, like this, this line does not pass any of these 3 points, but this is the best in the sense of least square. Now let's look at the variance. Variance means standard deviation squared. The variance predicted for the second data set. For the second data set, the line equals y equals x plus 1. So the predicted value when x equals 1, so x equals 1, 2, 3, the y predicted will be equals 1 plus 1 here, so equals 2. And when x equals 2, the predicted will be equals 3. When x equals 3, the predicted will be equals 4. Right? Let's see the variance of the predicted value. This is 2, 3, 4. And when we calculate the variance, we need to know the standard. We need to know the mean. The mean here 2, 3, 4. So the mean y bar predicted will be equals 2 plus 3 plus 4 divided by 3. Okay, that equals 3. Right? So this 3 is here, and the predicted value is 2, 3, 4. So 2, 3, and 4. And the variance is x minus mean squared plus x minus mean squared. Sorry, this is squared plus mean minus value x minus mean squared, then divided by a minus 1. Right? So this equals 1, this equals 0, this equals 1. Okay, this equals 2, then this equals 1. So the variance of the predicted equals 1. How about the variance of the observed? Right? The observed value is not 2, 3, 4. It is 1. Equals 1, 5, and 3. Right? For the observed 1, 5, and 3, the mean equals 1, 5, 3. The mean equals 3. And so the first one, the variance will be 1 minus 3, so equals 2 squared equals 4. Then this one, 5 minus 3 equals 2 squared equals 4, not 4. So 4 plus 4 equals 8. And this one here, 3 minus 3 equals 0, squared equals 0. So the sum equals 8. Then divided by 3 minus 1 equals 2, so equals 4. So this one equals 4. Okay? So the variance of the observed equals 4. The variance of the predicted equals 1. The variance of the observed equals 4. Right? This is the actual variance of the observed value. This one is predicted from the x, which is the variance of x. Right? Now let's see. The variance of x is only explains 1 over 4, 1 over 4 of the variance of the observed. How do we get this 1 over 4? 1 over 4 here. And that is exactly equal to x squared, r squared, r equals 0.5, and this one equals 1 over 4. Right? So that's obvious. R correlation coefficient equals 0.5, and 0.5 squared equals 1/4. And that exactly the variance of x, which equals the x equals x, is equal to the variance of the predicted y equals 1, and the variance of y observed equals 4, and only 1 of the 4 is explained. So that is r squared. Right? So that is for the second data set. Now look at the first data set. The first data set, and first let me make an assumption. Why we have a change in the predicted y value? Right? Can I claim that that is because of the variance in x? Looks yes, because all the points are on the line. So that is. So in this example, the r equals 1, so r squared equals 1. That means the variance of x 100% explains the variance in the y. And that's why all the points are on the line. So from these two examples we see, so r squared is the coefficient of determination, and its meaning is give us the percentage of the observed y value variance that can be explained by the variance of x. Okay, now some more examples of correlation coefficient of determination. The first one, we know this one here, r equals -1 because it's negatively correlated, and it's very strong. It's -1 here, like this. And r squared definitely equals 1. That means the variance in y will be 100% explained by the variance in x. So here, in this example, the larger the x, the smaller the y. No other reasons why y is smaller. The y is smaller is only because the x is large. It's 100%. In this example, the correlation coefficient equals 0. That means x and y has no relationship. X can change, but y does not change at all. So r equals 0, then r squared is still equals 0. That means the variance in x explains 0%. That means does not explain at all the variance in y. See, x changes a lot, but y does not change. What's the reason y does not change? Can be any reason, but the changes in x. So that's here. Now in this example, r coefficient, suppose correlation coefficient equals 87%, then r squared equals 0.76. Almost equal to 3/4. By the definition, we know the variance in x can only explain 76% of the variance in y. So let's see why the y value is large than this one. You may say, okay, probably because of the x value here is larger than the x value here. Is this 100%? No, this only 76%. There are some other reasons why this y value is larger than this one. There are other 24% due to other reasons. You may ask, what kind of other reasons? Okay, maybe the mistakes in the measurement, or maybe some significant other factors, we want to try to find the curve. But anyway, it's not because of the variance in x. The other 24% cannot be explained by the variance in x. The variance in x can only explain 76% of the variance in y. We mentioned the residual before. We have a data set in this scatter plot, and we have a least square regression line, and we have predicted value on the line for each x value. Here, 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 every value is on the line. And we use the observed data minus the predicted value. Here, observed minus predicted give us this. For this point, give us this. For this one, give us this. We call this as the residual, right? Because the distance to the line, or no matter what, so error or something. In this slide, we said it's called the residual. It is the contribution of individual data points to the overall pattern of scatter. Because of this schedule, so that's why we have a scatter here. If there's no this residual, then everyone is on the line, so there's no scatter. If residuals are scattered randomly around zero, the data fit a linear model, normally distributed, and there are no outliers. Look like this. This one here is the number of beers, is x. And the y value here is not the alcohol level anymore. It is the residual. So this, be careful. This is the residual. We only draw the errors or the residuals here. So for example, for the first one, when beer equals 1, the residual equals a negative. This is a little bit negative, so that's why it's here. When x equals 2, okay, residual equals 0, so that's equals 0. When x equals 3, we have two residuals. One is negative, another one is positive. So when x equals 3, one is positive, one is positive here, another one is negative here. Here. And we draw this. This is called a residual plot. This is called a residual plot. If in the residual plot, all these dots are randomly distributed, okay, that means there will be no outliers. So everyone looks like in the form. Examples of a residual plot. From the residual plot, we can find some mistakes or some errors in the data. For example, this is the residual plot. Keep in mind, again, horizontal is x, the y is not, y-x is vertical, is not the y value, it is the residual. If this looks like a very good residual plot. That means the residuals are randomly close to 0, but randomly around this 0 line. So this is good. And this one, the residual plot forms a curved pattern, like this. So that means your fitting line is not correct. In here, you may use a straight line. That means the form is not a straight line, not linear. I'll give you one example here. For this one, if we draw this, suppose we draw like this, the residuals here, suppose the line looks like this. That's our least square regression line. And the residuals here are negative. So that means all the point will be, the point will be here, so here. And maybe this one is on the line. And this one will be a positive. So these are positive, so it's like this here. And this one will be negative, so like this. So you can see this line cannot fit a straight line. It looks like maybe the line looks like this. It's not straight. If it's not straight, that's beyond the scope of our class, so we don't care. But anyway, from the residual plot, if the residual plot looks like this, then we know something wrong. most probably the relationship between x and y is not linear, it's curve. This one here, the variability, the variance change a lot with the increase of x. This one is still a linear form, linear relationship. That's no problem. But the problem is the data may have some mistake. So if the data is correct, but it's because of the big variance, if you use this one, even use the interpolation prediction, the error may still be large. So anyway, if you see a residual plot like this, you need to make sure, double check what happened here. Next one, we discuss outliers and the influential point. We already know outliers before, right? Outliers, observation that lies outside the overall pattern of observation. The new concept is called influential individual. Influential individual is observation that changes the regression line if removed. This is often an outlier on the x-axis. Here is an example. We use this example to show what the meaning of an influential individual. The data set are given in this scatter plot as this point, and it looks like this one here is an outlier. So outside this form, the form looks like here, linear form. This one is outside, and this one maybe. You may say this one is not outlier, it's still on the line. Yeah, looks like, but here we assume this one is outlier. Definitely this one is, but this one, yes, maybe not. So if I let you choose only one outlier, definitely this one. Choose two, maybe this one maybe not. But if we use the concept of a linear regression line, least square regression line, if we use all data, including this point and this point, so all data, the regression line is the red one. So the red one here in the middle, and this includes all data. And if we exclude this point, we do not use this point except this one. Try to find the least square regression line with all these other points, and that one will be 18, right? This one, it will be the dotted line, it will be this one. So this is without this point. And for this point, if we exclude this point only, and the regression line will be the black one, the black one here. The original line is this red one. Without 19, that is this black one. Without 18, that is this one. Compare these two situations. We can see point 18 has more influence in the regression line. So point 18 is the influential individual. On the contrary, this 19 is not. So this one is not influential point. This one is influential point. But this one is the outlier. This one may not. So what's the difference between 18 and 19? Look at this. This one looks an outlier. Okay, it's in the sense of y. Okay, this is y. The y is too large. And this one, outlier or not, are still in the form. But it definitely an outlier in the x direction. So this is x, all other x around here, but this x is too big. So this one is an outlier in the x direction. So that's why usually influential individual is an outlier on the x-axis. So next time in the scatter plot, if you see an outlier on the x, for example this one, or maybe another one here around this point, then most probably this outliers in the x will be influential individuals.